Hello everyone. Today I'm going to talk about the wafer level packagings. Before we go to the details about different type of wafer level packaging, let's have a quick overviews. What's the function of the wafer level packaging? Why we need the wafer level packagings? There are mainly two reasons. First is that in the IC circuit, integrated circuit, uh, different chips they need to communicating and connect to each other through input and output. The second reason is that all these chips they are very delicate and they need a protection, which is called packagings. There are different functions of the packagings. First is provide the power to the chips. Second is distribute the signal generated from the chips, and remove the heat generated from the chips. Finally, and support and protect our delicate chips. There are different type of wafer level packagings. The very earlier stage type of packages called PBGA, plastic ball grid array. Then there's a new type of packaging comes out, which is called a fan, and the newest one is called FOWLP, which is stand for fan out wafer level packaging. So the newest fan wafer level packaging have many advantages compared to the early stage flip chips PBGA, FC PBGA, which is that have a lower cost, lower profile, and will also eliminate the substrate, eliminate the wafer bumping, eliminate the flip chips reflow, eliminate the flux cleaning, eliminate the underfill, and it will have a better electrical performance, better thermal performance, and easy to go for SIP and the 3D IC packagings. And the advantage of fan out versus fan in wafer level packaging is that they use the known good die KGD, and they have the better wafer level yield, and usually use best of the silicon, and it can be applied to either single or multiple chips, and it can be embedded in integrated passive devices, and has more layers over audio redistribution layers, and they also have a high pin count and have a better thermal performance, and it's easy to go for a system in packaging and the 3D IC packagings, and they have a higher PCB level reliability. So what exactly is flip chip technology, the earliest generation wafer level packaging type? The simplest definition is that a flip chips is defined as a chip attached to the pads of a substrate or another chip with various interconnect materials and methods, as long as the chip surface is facing down or facing the substrate or another chips. There are different kind of interconnecting materials. The most famous is called C4 bump or C4 technology, which is stand for control collapse chip connection. The other type is called C2, which is called it's called copper pillar with solder caps. In both types, they will have the copper and the solders. In order to fabricate this kind of interconnection part, for example, let's say C4 bumps. First, we need to redefining the passivation for the pads, and then we deposit copper and tins all over the surfaces. Then we spin photoresisting materials on top of the wafers. Then we use a mask and UV light to do the patterning and etch away the center place. Then we use the electrochemical deposition method to deposit copper and solder sequentially into the holes. After that, in this process, we use a little bit more solder to form this kind of mushroom structures. After that, we strip away the photoresist. Then we etched away the copper and tin. The final step is do the flux reflowing to form this kind of well-defined shapes. For the C2 bump, it's a very similar process, but the only difference is that we use more coppers and less solder to form this kind of a higher pin and tighter pitch. So after we fabricate the bumps, either C2 or C4 bumps on the chips, we need to assemble. We do the assembling. So the general procedure for the flip chips assembly can be can have two types. One is called the indirect assembly. The other called direct assemblies. The bumping method we talked about before, they are like all like indirect type of bumping, because between the joints between the copper pillars there's solder attached, so that's why we call the indirect uh, assemblies. So general a flow chart for the indirect bumping is like this. So we flip the chips and use a camera to find the pin or pitch and align them with each other. Then we apply a high temperatures. Sometimes we also apply a high force to attach them together to connect them. Then in order to protect the pins, we have the underfills. Then after we form the underfill, we solidify them and make them a very stable and reliable devices. There are different type of underfill. The most commonly used is called the capillary underfill. There's also other type of the molded underfills. So again, underfill is a must. It will enhance the reliability of the flip chips solder joints. There are different kind of material in the underfill. The most commonly used is fused silica or a liquid type of pre-polymer like the thermosetting resins. Besides the indirect bonding, there's also some type of bonding called direct bonding or copper-copper direct hybrid bondings, which means we bond the metal pads and the dielectric layers on both sides of the wafer at the same times. The general procedure for the direct hybrid bonding is like this. First, we clean the surface. Next, we remove the metal oxide so that we have oxide free copper. Then after that, we activate the silicon dioxide or silicon nitride by wet cleaning or plasma activations. After the activation of the dielectric layer, silicon dioxide, silicon nitride, we do the first annealing at a relatively low temperature, around 100 Celsius degree to 150, to strengthen the bonding between the dielectric layers and minimize the stress inside the interface. Then we apply a higher temperature and higher pressure. Usually it's like 300 Celsius degree at 25 kilonewton in nitrogen environment for 30 minutes to bond the copper pillars. After that, we do some post-bond annealing at 300 Celsius degree and also at nitrogen environment for 60 minutes. Okay. Next, let's talk about another type of wafer-level packaging, which is fan-in wafer-level packagings. Fan-in wafer-level packaging is also called wafer-level chip-scale packagings. There's a unique feature for this type of packaging is that it use of copper redistribution layer to redistribute the fine pitch peripheral arrays pads on the chips of a wafer to a much larger pitch area arrays pads in the interior of the chips with a much taller solder bumps. By doing the packaging in this way, the demand on the PCB is released and the underfill might not be necessary. This figure shows typical structures of the fan-in wafer-level packagings, and the key step is written below. So basically, is follow the spin coating of the photoresist, and open photoresist and mask UV light, and doing the photolithography to open the vials and etch away the photoresist, strip away the photoresist, sputtering, coating and deposit metal layers, and then repeat different process to fabricate the redistribution layers so that we can transfer like we said, we can transfer the fine pitch on the peripheral array into the interiors from the array pads. Yeah. Another commonly used packaging type is called embedded chip packagings. So in this type of packaging, the chip is embedded in either laminated or polyimide panels, or in silicon wafer, or in glass panels. There's many advantage for the embedded chip packagings. First is that there's the cost is low profile, low cost with a very large panel, and they have a very good electrical performance with low inductance, and it's easy to extend to 3D chip stackings. The disadvantage is that it cannot be reworked. The infrastructure is painful, and also the supply chain is also pretty hard for this type of embedded chips packagings. So this is a typical figure of the embedded chips packaging. As we can see, the chip is embedded in dielectric layers with different vias. Finally, we can talk about the fan-out wafer-level packagings. So generally speaking, for fan-out wafer-level packagings, there are different fabrication processes. Generally, it can be divided into two types. One is chip first, one is chip last. In the chip first method, there's also two types. One is chip first and die facing down, and chip first, die facing up. The general process for the chip first die facing down is shown below. First, we need to for the device wafer, we need to be it need to be tested for KGD known good dies, then singulate into individual dies. After that, we put in the known good dies facing down onto two-side tape, two-side thermal release tape on temporary wafer carriers. Then the whole known good die on the temporary wafer carrier is molded with EMC epoxy molding compound. After that, we just gently remove the carriers and the tape, and in the last step, we can after removing the carrier and taper, we can build the redistribution layers and mount the solder balls, as you can see in step 5. So another type of the fan-out wafer level packaging is a chip first and die facing up. So in this type of fabrication, the process is shown below. First, we need to, as similar as the die facing down, we need the known good dies. Then the second step is that instead of using the tapes, the double side tape, we use a layer called LTHC, light to heat converting films. It's a temporary bonding materials. So after that, we can put the known good die on the temporary wafer carriers with the LTHC. Note that in this process, the dies are facing up, means the copper pad are facing up. Next step is we molded with the EMC, similar to the one before, but since the EMC very thick, we need to following that, we need to back grid the EMC to expose the copper pad for future electroconnecting. So after step 5, in step 6, we need to after we expose the copper pad, we build the RDO layer on this copper pad and the solder ball. Then we can, in the last step, we can remove the temporary glass wafer carriers using laser debonding techniques. So all the discussion above talk about the chip first, either die facing up or die facing down. There's another type of fabrication process in fan-out wafer level packaging is called chip last or RDO first. The reason for the existence of this type of fabrication process is that there are certain challenges of the chip first method, either die face up or die face down. Because the production yield during the RDL fabrication is pretty low. So if we do the chip first and then add the RDO layers, in case that is not working, the non-good die will be wasted. So that's why for some high-end devices, uh, people prefer to use the chip last or audio first process. So the key process in the chip last and audio first is shown below. First, we build the audio layers on a silicon wafer or some other kind of carrier, glass carrier wafer with certain sacrificial layers. So that in the last step we can remove this type of layer, either silicon wafer or glass wafers, use laser debonding technique. So after we build the redistribution layer using the standard process, spin coat photoresist, use stepper to develop an edge photolithography, then add deposited metals, and we can fabricate the audio layers. After that, we can attach the non-good dies facing down on the audio layers. Then we can have the underfills and add the EMC epoxy molding compound onto that for protection. Then after that, we can backgrade the additional EMC, then attach the reinforced wafers onto the non-good die. Then we can grade the silicon wafer or use the laser debonding technique to remove the bottom wafers if we use a glass carrier wafer with sacrificial layers. Then after that we can mount the solder bowl and dice wafer. So that's the standard process. So all the previously mentioned fan-out wafer-level packaging techniques are using the around 200 or 300 millimeter wafers as a temporary carrier for making the mold, audio, and so on. So in order to increase throughput, fan-out panel level packaging has been proposed. There are, compared to the fan-out wafer-level packaging, there are different type of advantages and disadvantages. The advantage is that compared to fan-out wafer-level packaging, fan-out panel-level packaging will increase the throughput and potentially lower the cost. However, there are many issues related to fan-out panel-level packagings, which should be noted and resolved. First is that since fan-out wafer-level packaging is well established, most of the foundry have the necessary equipment for fan-out wafer-level packaging. So for fan-out panel-level packaging, new capital need to be expended for equipment development. Next is that inspection of wafer is a well-known process for wafer-level packaging, but panel-level packaging haven't inspection or defect detection haven't been developed yet. So the yield of wafer-level packaging is higher than the panel-level packagings. And the cost advantage of the panel over wafer still need to be carefully determined. And a fully loaded high-yield wafer line will be cheaper than the partially loaded low-yield panel lines. Addition to that, the panel equipment take a longer time to clean because there's a lot of solvent or materials left inside the pipeline that is very hard to be cleaned. And unlike fan-out wafer-level packaging, the fan-out panel-level packaging is for small or to medium chip size and line-wise and spacing audio layers. And also there are only a few companies in the world that is capable of doing the panel level packagings. And there's the panel standards is lacking, so that's the equipment supplier cannot make the equipment. That's the major disadvantage of panel level packaging, but this area is still very promising and will be developed in the near